Hi everyone, welcome back. Today we're going to be practicing some curve sketching, and we're actually in order to do this, we're going to be putting together a lot of the knowledge that we've learned over the last several weeks. And we're going to put that into practice, and we're going to be able to sketch some pretty accurate curves based upon all the things that we've learned. Okay, when we want to sketch these curves, we want to go through kind of a checklist to make sure that we have a full picture and we gather lots of information about the function before we actually go and even try to begin our sketch. Okay, so the first thing we're going to do is we are going to determine our x and y intercepts. Okay, so of course we need to remember that in order to find that x-intercept, that is when y is equal to 0. And in order to find the y-intercept, that's the point when x equals 0. So f of 0. Okay, symmetry. Last year in pre-calc, you have learned about even and odd functions. And we know that even and odd functions tell us if the function is going to be symmetric to the y-axis or to the origin. And so we are going to test, of course, negative x in the function. And if it comes out the same as what we started with, then we know that the function is even and therefore symmetric to the y-axis. Okay? If, when we do f of negative x, it comes back the opposite of the original, then we know it's odd, which tells us it's symmetric to the origin. And that just helps us again with our sketch because it'll tell us what it should look like. If it comes back neither, then we know that it has no symmetry to the y-axis or to the origin. Okay, the next thing we're going to look for are our asymptotes, our vertical and horizontal asymptotes. So our vertical asymptotes, after we simplify, are when the denominator is equal to 0. So we always simplify, and of course any of those crossed out terms become the wholes. Okay, so the wholes come from, and you can kind of write your own notes in here for this one, wholes come from any of factors that get crossed out during the simplifying process set equal to 0. When you have the rational function that's remaining, if you set the denominator equal to 0, that's where you get your vertical asymptotes from. For your horizontal asymptotes, that, of course, is the limit as x is approaching positive and negative infinity. All right. Okay, next we take our first derivative. And we've learned over the last several classes that our first derivative tells us about intervals of increase and decrease. We've learned that if the first derivative is greater than 0, that we will be increasing, that f will be increasing. We've learned that if the first derivative is less than 0, then f of x is decreasing. Okay, we've also learned about relative extrema. We've learned that you will have a relative min when f prime changes from negative to positive. That would be a relative min. Okay, and if f prime changes from positive to negative, we will have a relative max. All right, last thing that we have to check for is our second derivative. And our second derivative, of course, communicates to us about concavity and points of inflection. So, once again, if our second derivative is positive, then that tells us that the original function is concave up. Okay, if our second derivative is negative, then that tells us that our original function is concave down. And if the second derivative changes sign at all, then we know we have a point of inflection. Okay, so let's go ahead and try this out with two different functions. So the first one we're going to try is f of x is x to the fourth plus 4x to the third. So like I said, we're just going to go through our checklist to determine all of the different things that we need. So the first thing on our checklist was the intercepts. Okay, we had the y-intercept and we had the x-intercept. Remember, the y-intercept is when you set x equal to 0. F of 0, you can tell right away. If you plug a 0 in, you're going to get 0 to the 4th plus 4 times 0 cubed, which is 0. So we now know that we have a y-intercept of 0. Okay, our x-intercept. Well, we're going to go ahead and make y equal to 0 and solve this function. Okay, that would tell me I would pull out an x cubed, and I'd be left with x plus 4. So we end up with x equals 0 and x equals negative 4. All right, so we have two x-intercepts of 0 and negative 4. All right, next thing we're going to go ahead and do is determine if we have any symmetry. Okay, and to do that, we are going to test f of negative x. So we test f of negative x into the original function. So we have negative x to the 4th plus 4 negative x to the 3rd. And that would end up being x to the 4th minus 4x cubed. So you can tell here that we are not the same as the original and we're not completely the opposite. So we would say neither, and therefore no symmetry. The next thing we need to ask ourselves about are there any asymptotes? All right, so when we ask that, we want to look at the function we have. This function is a polynomial function. So ask yourself, does a polynomial function have any asymptotes? And hopefully, of course, you know the answer to that is no. Okay, polynomial functions do not have any asymptotes. It's the rational functions, that's when you have a fraction with a polynomial in the numerator and denominator, that we need to be concerned about asymptotes. Okay, moving on. All right, so the next thing we need to do is go ahead and get that first derivative. Okay, so we're going to go ahead and write out first deriv. And so we here take the first derivative of this function and we would get 4x to the 3rd and then plus 12x to the 3rd. Okay, and we want to go through all the process of finding out the intervals of increase, decrease, relative min, and relative max. All right, so that means we need to find our critical values. So I'm going to go ahead and take this, factor out a 4x, oops, this should have been a squared, 4x squared, and I would be left with x plus 3. And so I get x equals 0 and x equals negative 3. All right, so I'm going to go ahead now and make my sign chart to look for my intervals. So f prime and f, I'm going to put negative 3 and 0 on there. Okay, and now I'm going to go ahead and plug in numbers back into the derivative. So if I plug in a negative 4, I would get positive times a negative would be a negative, so I'm decreasing there. Okay, if I plug in a negative 1, I would get positive times a positive, so a positive here, increasing here. If I plug in a 1, I get positive times a positive, so I'm increasing here. Okay, so we want to be able to make some conclusions. All right, we want to be able to say when are we increasing? So we can say that f is increasing between negative 3 and 0, and then also between 0 and infinity. And we would say that that is because f prime of x is greater than 0. We can also say that f is decreasing from negative infinity to negative 3, and that's because f prime of x is less than 0. We can also determine that we have a relative min at x equals negative 3. And that's because at x equals negative 3, we went from decreasing to increasing. Okay? You can see that at the other critical value, we continued to go from increasing to increasing. So that is not going to make a relative min or a relative max. So we don't actually have a relative max here at all. But what we do have is a relative min. Now, it would be helpful to actually determine the whole point for that relative min. Well, how do we do that? Well, we know our x value. If I want the y value on the original graph, how am I going to do that? Well, it sounds like I need to go back to the original function. Okay, so I want to determine what is f of negative 3. If I plug that back into the original, I get negative 3 to the 4th, and then plus 4, negative 3 to the 3rd. So this would be 81, and then plus 4 times negative 27, which is going to be minus 108. So that is going to give me a negative 27. So I know my relative min is specifically at the point negative 3, negative 27. Okay, now I'm ready to go on and look at my second derivative. Okay, so if I remember correctly, the first derivative was 4x to the third plus 12x squared. So my second derivative is going to be 12x squared plus 24x. Okay, and once again, I should be able to factor out. I need to find my critical value, so I can factor out a 12x, and I'm left with x plus 2. And so I end up with x is 0 and x is negative 2. All right, so now again, I need to do a sign chart. So this time it's f double prime and f, and I have negative 2 and 0. All right, so those are my zeros. And so I test some values, again, into the second derivative. So if I tested negative 3, it would be a negative times a negative again, which is positive. So, oops, I don't want to do the arrow. I want to do concave up. All right, negative 1 would be a negative times a positive, which is negative, so concave down. And positive 1 would be positive times a positive, positive, concave up. All right, so I'm ready to make some conclusions again from this sign chart. I'm able to say that I am concave up from negative infinity to negative 2, and again from 0 to infinity. Okay, and that was because f double prime is greater than 0. I can say that I'm concave down from negative 2 to 0, and that's because the second derivative is less than 0. I can also see that I have 2 points of inflection. I have points of inflection at x equals negative 2 and x equals 0. Now remember, when I have these points of inflection, just like with the relative min and max, I want to find out what the whole point is. Because if I'm sketching it, I want to see what the x and the y value is, so I know where to sketch it. All right, so again, I'm plugging those values in to the original so that I can get points for the original graph. Okay, so this means I'm going to go ahead and find out what's f of negative 2, which would be negative 2 to the fourth plus 4 times negative 2 to the third. So this would be 16, and 4 times negative 8 is minus 32. So I get negative 16. So my point here is negative 2, negative 16. And then f of 0 is much easier. We already know that that's 0. So this point here is 0, 0. All right, so now I've gathered all of my information, and it's a lot, okay? So I am now ready to start making my sketch. Okay, so I made myself an x and a y axis, and I did put a slight scale on my x-axis, just counting by ones. I don't usually put any tick marks on my y-axis, because if you look at those y values that we have to plot, we're talking about negative 27, negative 16. I'm not going to go ahead and scale that. I'm just going to plot those points and name them when I get there. Okay, so the first thing you want to do is go back through your checklist and just kind of get as many points on your graph as you can. All right, so first thing we're going to start is with our x and y intercepts. So we learned that we had a y-intercept of 0. So I'm going to go ahead and plot on here that I have 0, 0. Okay, we also had a x-intercept of 0 and of negative 4. So 1, 2, 3, 4. I'm right here. Okay, so I have my x and y intercepts. The next thing we looked for was symmetry. There was no symmetry. The next thing we looked for was asymptotes, and there was no asymptotes. Okay, so then we are down to our intervals of increase, decrease, and more importantly for this beginning part is our relative mins and maxes. There was no relative max, but we had a relative min at negative, what was that? Negative 3, negative 27. So I'm going to go back 3, and I'm going to go pretty far down and just make a point here, okay? And I'm going to label it negative 3, negative 27, and I might also put underneath it min, okay? Next thing I want to have are my points of inflection, because I did my second derivative. Okay, and I'm going to go ahead and get my two inflection points, which were 0, 0, which we already have on there, but I'm going to mark it as a POI. And I also had -2, -16. So I'm going to get that on there and mark that as -2, -16, and also put POI. The next thing I want to do is talk about those intervals so that I have a clear idea of what my graph is going to look like. And before I write anything down, I really want to make sure that I understand what's happening and kind of sketch it out first with, with just my finger before I go ahead and draw anything in. So you can see here that I was increasing between -3 and 0, and then again between 0 and infinity. Then I'm decreasing between -infinity and -3. Okay, so what does that mean? That means that I need to be going let's start with this first interval from -infinity to -3. That's telling me that I should be going down. But remember, there are two different ways to be going down. I can be decreasing and be concave up. I could be decreasing and be concave down. So which one is it? Well, that's when I need to come over here and decide that from -infinity to -2, I was in fact concave up. So that tells me that it's going to look something like this. All right, so I can go ahead and graph that part in. So I'm going to be coming, and and that's a relative min, so then I'm going to come back around, and I'm concave up all the way until I get to -2, -16, which was a point of inflection. At that value, I switched from being concave up to being concave down. Okay, and you can see that that's because right here, I switched my concavity. So I'm going to go ahead now, and it's just going to kind of reverse and go like this. Not very much, it's not a huge difference, but just a little bit. All right, now I am concave down up until 0. At that point, I am going to go ahead and continue to be concave up again. And so what's going to happen is it's going to reverse back and come up like this. All right, so if you notice, we were increasing everywhere after -3, so it makes sense that I just keep going up. But first I was going up, increasing but concave down. Then I was increasing but concave up. All right, so the last part of my graph is going to look like this. All right, so kind of look that through and make sure you see the differences. All right, so here's a picture of how you can have a point of inflection, but not have a difference in increase and decrease. Sometimes people call those a saddle or a plateau, where it kind of levels out a little bit and then it comes back around. So that's our first one, all right? Look that back through, make sure you understand why we have every part of that graph as we do, and we're going to go ahead and try one more. Okay, the second function that we're going to look at is a rational function. So we are going to go through the same list of checkpoints as we did for the polynomial function, but we're going to definitely see some different nuances. Okay, so we do have 2x squared divided by x squared minus 1. So the first thing we want to do with a rational function is ask ourselves, can we simplify anything? All right, so we always want to go ahead and try to factor it. So if you notice, the numerator cannot be factored. The denominator can be factored into x plus 1, x minus 1. So nothing cancels, but that's going to help us out, just get us set up for later. All right, so the first checkpoint is to go ahead and find our y and x and y intercepts. So my x-intercept is when I force y to be 0. So I'm going to go ahead and say 0 equals 2x squared over x squared minus 1. All right, of course this is only going to be equal to 0 when the numerator equals 0, because if I were to cross multiply, all right, I get 2x squared equals 0. So 2x squared equals 0. So x is just going to be 0. All right, now my y-intercept. All right, so the y-intercept is when you put a 0 in, so g of 0 equals, that would be 2 times 0 would be 0 over anything is going to be 0, as long as it's not 0 over 0, which it's not. All right, so 0, 0 is our only time when this function crosses the x or y intercept. All right, the next thing we're looking for is if it's even, odd, or neither. All right, so we're going to check our symmetry. All right, so f of negative x equals, so I'd have 2 times negative x squared over negative x squared minus 1. All right, well, if you notice, both of those are going to stay the same. So that tells us we have an even function, and so we have symmetry to the y-axis. Okay, so that is going to give us a good hint about what this is going to look like as I graph it. All right, next thing we're looking for is our asymptotes. So clearly when we have a rational function, this question becomes much more alive. All right, so we have different types of asymptotes. And we also should think about if we had any holes. Because when we simplified it, nothing crossed out, we do not have any holes, we can jump right into the asymptote. So there's no holes. All right, so asymptotes. All right, we can say that there's no holes. All right, vertical asymptotes. So vertical asymptotes are when the simplified fraction, we take the denominator and set it equal to 0. So clearly we can say we have x equals -1 and x equals 1. All right, the next thing is our horizontal asymptotes. And our horizontal asymptotes are going to communicate to us about the end behavior. So the limit as x is approaching positive and negative infinity. Okay, so we can see here that the limit as x approaches infinity of this function of g of x, well, because x squared and x squared on top and bottom, so we're just going to take the ratio of the coefficients, would be 2. And when I put in infinity over infinity, I'm going to get a positive 2. The limit as x approaches negative infinity of this function is again going to be 2, and because it's squared over squared, the sign is not going to change. And so we end up with y equals 2 as our horizontal asymptote. All right, so we're going to move on now to that first derivative. Okay, so we need to take the first derivative of the function. So I recopied the function down for myself. All right, and so clearly it's a quotient, so I'm going to use the quotient rule. So the first derivative is equal to low d high minus high d low all over low squared. Okay, so if I clean up the top, I'm going to have 4x to the third minus 4x minus 4x to the third. And so that's nice because the 4x to the thirds cancel out. And so we end up with a first derivative of negative 4x over x squared minus 1 to the second. Yep. Okay. So remember, when we have a rational function and we're talking about our critical values, we both have to set the numerator and the denominator equal to 0. Okay? So if I say negative 4x equals 0, I get x equals 0. Then moving on to the denominator, I'd have x squared minus 1 equals 0, so x would equal positive and negative 1. All right, so setting up my sign chart, first derivative, f. I'm going to go ahead and put those three values, negative 1, 0, and 1. Now, negative 1 and 1 are going to be, does not exist, and then 0 is your 0. All right, so as we go through and test, we can see negative 2 is going to be a positive on the top, over. Everything is going to be positive on the bottom because you're going to have a squared. So positive over positive is positive. That's increasing there. Oops. All right, negative 0.5 would as well be positive over positive, so positive increasing there. All right, at positive 0.5, we're going to have a negative on the top, positive on the bottom, so negative decreasing there. And at a 2, it's going to be negative over positive, so negative decreasing there. Okay, so we're ready to make some conclusions. We're ready to say that f of x is increasing from negative infinity to negative 1, and again from negative 1 to 0. And obviously that was because f prime of x is greater than 0. We can say that f of x is decreasing from 0 to 1 and from 1 to infinity, and that's because f prime of x is less than 0. Okay, we can determine that we have one relative value, and that would be a relative maximum, because this time, if you look here, we are going from positives to negative. So when f prime changes from positive to negative, we go from up, increasing, to decreasing. And so we're going to have a relative max when x is equal to 0. Now, what is that value? Again, we plug that in, and we've already figured out f of 0. We plug it back into the original, is 0. So our relative max is at 0, 0. Okay, I'm moving on to find the second derivative. Okay, and I left my first derivative right here so that I could see it. All right, so my second derivative is low, so this time it's x squared minus 1 squared. D high is negative 4 minus high, which is negative 4x. D low is going to be 2 times x squared minus 1 times 2x. All over x squared minus 1 squared squared is to the 4th power. Okay, so let's try and simplify this ugly beast. Okay, so the second derivative is negative 4 x squared minus 1 squared. Negative times a negative is going to be a plus. 4x times 2x is going, 4x times 2 times 2x is going to be 16x squared, and then x squared minus 1 all over x squared minus 1 to the 4th. Okay, I'm going to go ahead, and I recognize that in the numerator I can factor out I'm going to go ahead and take out a negative 4 and an x squared minus 1 from both terms. So I'd be left with x squared minus 1 for the first term, and then minus 4x squared for the second term, all over x squared minus 1 to the 4th. Okay, as I clean that up, I can tell that inside this bracket here, what's left over, I can make that negative 3x squared minus 1. Okay, and then I also can tell that I can cross out this x squared minus 1 with one of these down here, so this is going to become a cubed on the denominator. Okay, so last step to clean it all up, I'm going to go ahead and distribute that negative 4 through. So I'd get 12x squared plus 4 all over x squared minus 1 to the 3rd. Okay, so now I'm ready to find my critical values. All right, normally I would set my numerator equal to 0, but if you look at this, I have 12x squared plus 4. That's always going to be positive. It's never going to equal 0. The only time it would equal 0 would be for some i's, which I'm not, from some imaginary values, which we're not concerned with. So I can kind of skip the numerator and go right to the denominator and do the x squared minus 1 equals 0, which of course I know is positive and negative 1. Okay, so when I do my sign chart, I only have to put those values on there. And those, again, were from when it was undefined. All right, so testing those into, remember we said the numerator is always positive. And so, let's see, negative 2, it's going to be a positive over, so that would be 4 minus 1 would be positive, cubed would be positive. So I'm going to be concave up there. All right, then I'm going to go ahead and test 0. So that would be positive over. 0 minus 1 would be negative 1. Cubed would be over a negative. So that's going to be concave down. And then I'm going to test a positive 2. And again, that's going to be positive over positive. So concave up. All right, so my conclusions are that that f of x is concave up from negative infinity to negative 1 and from 1 to infinity. And that's because the second derivative is greater than 0. I am concave down from negative 1 to 1, and that's because the second derivative is less than 0. Normally at this point we would be talking about points of inflection, but I want you to think about what we know about when x is equal to negative 1 and positive 1 that we learned earlier. if you remember, we have vertical asymptotes at x equals -1 and +1. So there's no way we could have points of inflection there. You can tell that they are undefined there. And so there is no points of inflection here because of the fact that our only places where we would change from concave up to concave down, those aren't going to be points because they're not defined. So no points of inflection because we'll have vertical asymptotes there. Okay, to finish this up, I'm ready for my sketch. So I just made a recap up here of everything that I learned, okay? And that's what I have written up here just for myself to talk through this. So as we said before, all right, the first thing to get on there are those x or y intercepts. So I'm going to go ahead and plot 0, 0. All right, then I would want to get on there my vertical asymptote, my horizontal asymptote. So I can have vertical asymptotes here at x equals -1 and x equals +1. I also see that I have a local max at 0, 0. So I'm going to mark that as a max as well. Okay, that's my only point. So I really have to use, oh, and I also have a horizontal asymptote, at y equals 2. So that really, you know, of course, communicates to us about our end behavior. Get rid of some of these lines. Okay, so I'm just going to kind of look at my intervals and talk about what I'm doing. From -infinity to -1. So over in this area over here, it says that I am going up. I am increasing. So, and I'm also, if you look here, I'm concave up. Okay, so that's super important because I have to be increasing and also concave up. So I know it has to look like this. Well, but I also have this horizontal asymptote, which tells me my end behavior on the far left-hand side is going to flatten out at 2. So in order to flatten out at 2, I'd either have to look like this to flatten out at 2 or like this. Well, which one of those two options is concave up? That's right, the first one was. So this is what this graph is going to have to look like. Okay, now likewise, I can also tell that I was decreasing from 1 to infinity. On the other side, I also remember way back, I know that I have symmetry over the y-axis. So whatever I did over on that corner, I'm going to also do over here. And let's just make sure that that follows. Am I decreasing from 1 to infinity? Yes, I am. But am I still concave up? Yes. So once again, I am concave up, but I'm decreasing. All right. Now what's happening in the middle? What's happening between -1 and 1? Well, you can see here that I am between -1 and 0, I'm increasing, and between -1 and 1, I'm concave down. So I'm concave down for this entire interval, but I'm increasing to a max, and then I decrease. So that's pretty plain to see that I'm going to increase here to a max, and then decrease back down in between my vertical asymptotes. Okay, and again, showing that symmetry on the y-axis. So you can see that without gaining any other points, only one point I knew on this graph, I was able to sketch a complete graph of my rational function. All right, thanks so much for sticking with me. I know these were two very long problems, but I think it's a great wrap-up of a lot that we've done over the last couple weeks, and it's a great skill to be able to have. Similar to what you did last year, we did a lot of sketching of graphs last year, but this is definitely using the derivatives as opposed to using so many other points. Okay, thanks so much, and I'll see you next class.